let's start with the history of magnetic sound recording. In 1900, this guy is Vladimir Poulsen. He demonstrated a telegraphone, a device to record sounds onto a steel wire. After 35 years, in Berlin, Fritz Fliehmer demonstrated a magnetophone. It is the first recording machine to use magnetic tape to preserve voice. And then, IBM markets the first magnetic tape drive, which is named IBM 701 tape drive in 1952. It was then adapted to IBM's first commercial computer for data storage. It was able to record 7,000 characters per second. Now, let us look at the comparison between ancient tape and modern tape. For 701 tape, it has tape width of 13 mm and 7 data recording tracks. Whereas Fujifilm Ultra-EM cartridge has tape width of 12.56 mm and 2,176 data recording tracks. Next, we are going to show you basic audio recording. This is a raise head. It uses AC field with frequency several times higher than maximum audio frequency to demagnetize the tape. Next is right head. An audio frequency voltage is used to generate magnetic field, which then the stray field magnetizes the tape. And finally the reed inductive head. Stray fields from the tape will magnetize the yoke. The varying audio signal is detected by magnetic induction principle. It usually has more coil turns than right head. Now, let us show you the digital magnetic recording. The data is stored on the tape by magnetizing the tape to the saturation. There are two possible states of the given tape area depending on the polarization of the input signal from the right head. The states are 0 and 1, which represent digital data that can be processed by computers. Reading of digital data from the tape can be performed with inductive head as previously shown for basic audio recording, or with magnetoresistive heads using anisotropic magnetoresistance, AMR, or the giant magnetoresistance, GMR. So where are the bits? In digital recording, bits which longitudinal or perpendicular, they are written into the tape or disc in the form of areas. They usually single magnetized area encompasses many grains. The more grains, the sharper transition between neighboring magnetized areas can be achieved. For years the increase in the storage density, which is the number of bits that can be stored on unit surface, was achieved mainly by a decrease of grain size. The magnetic field produced by a line of magnetized bits is characterized by changes of field direction corresponding to transition between areas of opposite magnetic moments direction. For your notice, the magnetic inductions, which are the B lines, are schematic and simplified. They are calculated assuming that the area of the storage medium where the bits are stored and consists of parallelepiped with magnetization exactly parallel to x-axis, which is constant throughout the whole bit. Magnetic induction strongly decreases with the distance from the surface of the storage medium. The X component of magnetic induction changes sign in the vicinity of the transition between oppositely magnetized regions. Due to the strong dependence of the stray field strength on the vertical distance from the medium, the gap between the reading head and the tape or disc must decrease with increasing bit density. In electronics, in the presence of external disturbances, noise, to register the change of a voltage is faster than to determine its value. Consequently, the bits are read not as a value of the magnetic field associated with a magnetized region but as its change. This is equally true for the readout with inductive heads, where the signal is proportional to the tape or disc speed, as well as for magnetoresistive heads, AMR, GMR, TMR, where the resistance is read out as a voltage from a field sensor. There are many ways of encoding data by series of flux reversals. So here, there are two examples shown. For RKKY coupling and saturation field, in a general case of unlike layers, which is the different magnetization, anisotropy energy, anisotropy direction, coupled by interlayer coupling. There are no analytic expressions available for a direct comparison with the experiment. For simple cases, the expressions describing a hysteresis loop can be found in literature. For the simplest case of two identical layers, the saturation field can be found as follows. Here, we are interested in the case of F coupling when J less than 0 and want to find the Th1mu0H. In the case of multilayers composed of identical layers, the saturation field is expressed by a different equation. Bs equals mu0 Hs equals 4J divided by M. If the anisotropy is present, shapes of hysteresis loops can be complicated and strongly n-dependent, at least for small n. For the field sensitivity of magnetoresistance, we know that the RKKY-like interlayer couplings strongly decrease with the spacer thickness Ts. The saturation field of the GMR effect depends consequently on Ts, but the GMR amplitude decreases with Ts. In the figure, the low field region of magnetoresistance for the same sample is demonstrated. The thick straight line indicates the slope of GMRH dependence. Besides, the highest sensitivities in GMR and DMR systems are obtained with spin valves or pseudo-spin valves. GMR. First we're gonna talk about field magnitude sensors. The most important characteristics of field sensors are sensitivity and linear range. Moreover, in many applications the linearity is not important, as only the resistance change between two defined states is measured as the presence of an object or current direction of the field angle of rotation. From the graph we can see that the resistance change in the linear range of the RH dependence is related to the reversal of the iron-nickel layer. The saturation field is determined by the shape anisotropy of iron-nickel layers. In hysteretic range, it is not useful for applications, because both cobalt and iron-nickel layers' magnetization directions change. Next we're gonna talk about field magnitude sensors with memory. From the figure we can see that wedged cobalt layer shows a monotonic decrease of the coercive field with increasing thickness because the contribution of the perpendicular surface anisotropy diminishes. The resistance of the stack after the removal of magnetic field at remanence is a linear function of the maximum applied field. Next is angle sensor. It is used to fabricate a sensor of magnetic field direction. One can use a single spin valve. It is assumed that the magnetic moment of the free layer is parallel to the field direction. Below is the related formula. As we can see, the current through the R1 and R3 resistors is given by. The voltage above the resistor R3 is given by. And for bridge output we have. From the graph, we can see if the sensors are different, the output may be not symmetric relative to 0. Thirdly, we're going to talk about GMR current sensors. The field produced by a current flowing through the wire can be sensed with magnetoresistive elements, and they offer better sensitivity as compared to Hall effect-based sensors. The sensors are fabricated so that the current conductor is integrated into the device. Furthermore, we have GMR-based sensors with storage functionality. In some applications the angle detection capability should extend to n turns of the field. The applications could be in steering wheels, potentiometers and motor feedback systems for industrial applications. Next is the magnetic beads detection with GMR. From the figure, the patterned nickel iron cobalt 6 nanometer GMR sensors deposited on silicon substrate. For the figure below, the resistance of that part of the sensor is reduced due to a presence of stray field from a bead. Magnetoresistive random access memory, MRAM. Magnetoresistive random access memory, based on magnetic tunnel junction bits, is a promising scalable non-volatile memory that may have unlimited read and write endurance, high-speed read and write operations, and low power consumption. The first magnetic random access memories used ferrite rings to store bits of data. To write a bit, the magnetization of the cores was switched by a combined action of currents flowing in wires woven through the toroids and the readout. It was performed by registering the voltage induced in a wire by the application of the definite impulse in writing wires. If we want to store some data using the magnetic elements, the bits can be encoded into the orientation of magnetic moment of thin films patterned, so that one bit is contained within one island. In order to read the data, we use magnetic induction effect in core memory. To use magnetoresistive effect in the readout, we may need additional magnetic layers. Using spin valve principle, we can determine the orientation of green moments by measuring the resistance of the stack containing both types of layers. Red layers have higher coercive field due to exchange coupling to antiferromagnet. Writing of data into the single memory element requires either the application of a magnetic field, which is strong enough to reverse the magnetic moment of the free layer, or the use of a spin-torque transfer effect to achieve the same effect. In the diagram we can see, normal, not spin polarized, current flows into the polarizer. Where it becomes polarized, polarization is less than 100%. Spin polarized electrons travel to the analyzer, which is separated from polarizer by a spacer, where they polarize according to the magnetization of the analyzer. The memories utilizing the latter effect are called STT, MRAM. These types of memories are more attractive than memories using magnetic field for magnetization switching. It is because they do not require additional field conductors, and energy required to switch the single bit is lower. To read the resistance of a given cell, the resistance between the appropriate column and row is measured. There are numerous sensing schemes, which can be used to decide whether the given resistance corresponds to 0 or 1. Some of the schemes involve comparing resistance with a reference cell of an O state. MRAM, magnetic field. To produce the magnetic field, which is spatially selective, different arrangements of conductors can be used. The most obvious is the use of crossed conductors, usually stripes. The magnetic field created by the single line is too weak to switch the magnetization of the free layer. Combined action of two conductors creates the field, which is strong enough to switch the moment direction of the memory cell. In the diagram, the arrows show the direction of magnetic field, not magnitude. Diagram on the left is magnetic field with one conducting wire, while diagram on the right is magnetic field with two crossed conducting wires. Note that the small area is the area with highest field values. So now, we are going to talk about spintronic devices. But, what is spintronic? Basically, the word can be interpreted as combination of spin and electronic. Spin is a rapid turning motion, while electronic is a study based on measuring the tiny electrical charge of electrons passing through electronic circuits. By combining both of them, we get spintronic. Spintronics, which instead relies not on electrons' charge, but on another of their fundamental quantum mechanical properties, spin. Spin can be visualized as the Earth turning on its own axis while rotating around the Sun. In the same way, an electron spins on its own axis while rotating around an atom's nucleus. Spin is either up or down. Same as traditional electronics uses charge to represent information as zeros and ones, the two spin states can be used to represent the same binary data in spintronics. The spin can be represented by a vector. For an electron spinning west to east, the vector points north or up, and it points down for the spin in opposite direction. Spin can be measured because it generates tiny magnetic fields. Ferrous metals such as iron become magnetic, for example, when enough particles have their spin set in the same direction, generating a magnetic field of the same polarity as the spin. Spintronics has several advantages over conventional electronics. Electronics require specialized semiconductor materials in order to control the flow of charge through the transistors. But spin can be measured very simply in common metals such as copper or aluminium. Next, less energy is needed to change spin than to generate a current to maintain electron charges in a device, so spintronics devices use less power. Third, spin states can be set quickly, which makes transferring data quicker. And because electron spin is not energy dependent, spin is non-volatile. Information sent using spin remains fixed, even after loss of power. All spintronic devices act according to the simple scheme. Information is stored or written into spins as a particular spin orientation, either up or down. The spins, being attached to mobile electrons, carry the information along a wire. Spin orientation of conduction electrons survives for a relatively long time, which makes spintronic devices particularly attractive for memory storage applications and quantum computing, where electron spin would represent a bit of information. As summary, magnetoelectronics, spin electronics, and spintronics are different names for the same thing: the use of electrons spins in information circuits. That's all for our presentation. Thank you.